I did happen to have in my bag is some information on the Portland Clean Energy Fund, and it passed in November. So when it ramps up to full force in about 5 years, it will have about $80 million each year to spend on clean energy projects and energy efficiency programs, job training in the low income and communities of color communities. And this 2020, it will have about $30 million to spend. It will ramp up to a committee of 9 members that the Portland City Council will appoint. Each city council member will have one person that they appoint. So that's a total of 5 people. And then those 5 people will get together and appoint 4 more. So there will be a 9-member committee. And it's funded by a tax, a 1% tax on large retailers, those with gross revenues nationally exceeding $1 billion and $500,000 in Portland. They'll pay a surcharge of 1% on gross revenues from retail sales in Portland, excluding basic groceries, medicines, and healthcare services. It will have an emphasis on renewable energy and energy efficiency projects that benefit low-income individuals and low-income communities and communities of color. It's got a skills training and workforce development aspect, also for economically disadvantaged and traditionally underemployed workers. And it's got provision for funds, including urban tree canopy, because the best way to sequester carbon in the soil is through trees. The tree roots are especially good at sequestering carbon in the soil. And also agricultural practices that increase the capacity of the soil to store carbon and reduce.
Most of us know Laurent Beauregard, not only because of his membership and contributions to HGP, but also because he just gave part 1 of this presentation on explanation and understanding in science 3 weeks ago. But for those of you who may be here for the first time or missed part 1, Laurent holds a Ph.D. in the history and philosophy of science. His primary through secondary education was in Catholic schools, where he felt he got a good education, but always had his doubts about miracles and mysticism. When he left the faith for good, however, he did it without blame or rancor. As he puts it, he was willing to let bygones be bygones, and eventually found humanism, which he sees as godless living in as understated a way as possible. He's not much of a t-shirt or bumper sticker kind of guy. What he is, of course, is a science guy. Having cogently explained the transition from Aristotelian to Newtonian thinking last week, he will move on today to Albert Einstein's early 20th century achievements in the theory of special relativity. The result was a view of the universe that went beyond Newton in a singularly interesting way. Please give a warm hand to Laurent Beauregard.
In part 1, I wore a t-shirt that had Newton's second law on it in a calculus kind of way. Didn't mention calculus at all 3 weeks ago. I will be mentioning calculus today, but I won't be doing any derivations, and there won't be anything to do with trying to, go from one equation to another. But I did feel forced to flash some equations at you toward the end in order for us to be able to see form, and you'll see how that comes out when we get to that. Now, explanation and understanding, I should probably explain a little bit about how I take explanation and understanding to be. I did this in part 1, and what we talked about then was the transition from Aristotle to Newton, and that transition occurred over a period of 2,000 years. The Aristotelian way of thinking, as you remember, was appeal to purposes and essences. And by the time the 17th century came about, that was being dropped in favor of explaining in terms of causes. And as you'll see in a couple of slides, mathematics was very much involved. The thing that I did not mention in part one was that when it comes to explanation, it depends on what you're trying to explain. If you're trying to explain something that's going on in physics, these are phenomena that don't have any purpose to them. Now we know. Heat, light, sound, waves, none of it has any purpose at all. So the manner in which we try to explain these things has a lot to do with the nature of the beast that we're looking at. Suppose we're trying to explain a poem. Suppose we're trying to explain a work of literature. Totally different thing. There is purpose involved there in the product. There is intent involved, motives, whatever. Put all that human stuff into it, and what you're looking at when it comes to trying to explain it is going to be a mode of explanation. You might call it, you want to get fancy? Hermeneutics. You want to get non-fancy? Interpretation. And so these things, these works, these human works, are things that are subject to interpretation in a way in which it would be something slightly absurd to think that you need to interpret the motions of the planets or the rippling of the waves here and there and some. All of those things don't have anything there for you to interpret. You might say, well, interpretation is going on in terms of when you make up theories that are going to be talking about these things, and certainly the theories, which are human products, are subject to interpretation, but not the phenomena themselves. In the old days, you did think that there was something going on that was purposeful. So I just wanted to point that out because on the way over here, driving over here, we saw lots of people on their way to church. And they're going there in order to get explanation and understanding of sorts, but not the kind that we're going to be doing here this morning. So the question that you're going to be asking yourself in the course of this presentation is, how much science and reason can I take this morning? And because that's what one of the four things that humanism is about, is science and reason. So, having said that, so we'll start. This is just a slight review, but there's something added here. And what's being added here is this term here, which I didn't talk about very much last time. So this is what I was just talking about, the transition going from Aristotle to Newton, going purposes and essences. Mentioned that there's no predictive value in doing explanations like that. You just say what you think is going on, and there's no predictions involved. But when you invoke causes in mathematics, then that does make prediction possible. And you can almost kind of like get a sense of, I mean, if you put something down in the form of an equation, and it's a mathematical law, and you're applying it to something, then you've explained what you're trying to explain. But if you've got something that's really rich, the law that, or the theory that you're using will have a predictive import, and you'll be predicting things that you didn't know before. So that's that transition. And the other transition, of course, is from, well, not of course, this is what's new this morning. We're going to go from Newton through Maxwell, very important 19th century scientist, did his work about the same time as the US Civil War was going on. And we're going to get to Einstein, but it won't be too much Einstein. It'll be just enough Einstein in order for you to feel satisfied that we got something accomplished this morning. And the something that I want to accomplish has to do with the phenomenon of unification. This, I think, is the key to when you have a deep explanation. You see not only that it involves the possibility of prediction, but that it unifies things that you didn't think were connected before. This morning I'm going to be talking about electricity and magnetism, and for the longest time, during those 2,000 years, people knew about electricity. You know, you rub certain things together and there's static electricity. Benjamin Franklin knew about electricity. You know the story about Benjamin Franklin. Somebody told him to go fly a kite, and that's what he did in a lightning storm. And it was kind of a dangerous thing to do, but Benjamin Franklin discovered that lightning was an electrical phenomenon. But I don't think he had any clue that it had anything to do with magnetism. Magnetism was something else. So you had electricity and magnetism. When Maxwell comes along, you get those two things unified. And that in itself is quite an accomplishment. To get one discipline and then another discipline unified together, and that increases your understanding of what's going on. But that's not even the last word on Maxwell. And you'll see what that is when I get to it. So, unification. Next one. What happened in the 17th century, and I mentioned some of this before, but I've added something here. I don't think I talked about Descartes last time. Very important. 17th century, an incredible century in intellectual history. This is the time not only of Galileo and Descartes, but it's also the time of Leibniz. Descartes. So I've got these quotes here in order to illustrate the importance of the transition to mathematics. Galileo actually wrote this: to understand the universe, you must understand the language in which it is written, and it's written in the language of mathematics. I almost apologize for including that there, but that's what he wrote as well. Descartes. Now, Descartes' the one who invented analytic geometry. I mean, a brand new branch of mathematics. Never mind that he was the father of modern philosophy. You can verify that by using Google and other ways. But he actually invented that. But he had a... Now, I have to say this about Descartes. If we're talking about physics, Descartes was a physicist. And he had a theory about how matter works in space. And he thought that all of space was filled with matter of different kinds and operated in... He had a theory about vortices. He had a really, really crazy theory that turned out to be all wrong. But it was him. It was Descartes. And Descartes said, good old materialist was he, give me matter in motion and I will construct the universe. Now there's an attitude. So, two things are going on: transition to a materialistic philosophy and a transition to the use of mathematics in order to effect explanations. Now, speaking of materialism, the typical thing that's going on here is that you have, I'll be talking about space quite a lot, absolute space, this big container. What's going on in the big container? Bits of matter, and they interact. But how do they interact? Well, obviously, mechanistic materialism means is that they interact the way billiard balls do. So that's action by contact. And just think Joe Biden here. Now, action... Can't believe I said that. Now, the thing about that was that Newton had put forth a theory of gravitation that was that, action at a distance. How can that be? If you're a materialist, how can you have two things separated by space interacting with one another? And people actually approached Newton and said, how can this be? And he said, look, I think I mentioned this once. He said, hypotheses non fingo. He spoke Latin every once in a while. And hypothesis means I feign no hypotheses. In other words, what do you want from me? I gave you the equation. The equation was. So, absolute space and absolute time. And these are quotes from Newton's work. Absolute space, in its own nature, remains similar and immovable without regard to anything external. And the same kind of thing about time. An absolute time stretched from the infinite past onto the infinite future. So you had those two continuums, the space and the time, and they're both absolute, and they are the grand stage on which all physical phenomena happen. Very important to again, God comes into the picture, but it's not really part of the physics. It's just part of the way they spoke. Newton actually described absolute space as the sensorium of God. That's about space. And about time, it's important to mention that part of the notion of absolute time. This is very, very important to see when we come to Einstein. Distant simultaneity was absolute. That means that if something is happening here, and if something else is happening over there, and when I say over there, I mean way over there, like light years away, if time is absolute, then the notion of this happening at the same time as that over there is objective. Einstein gives that up. No such thing as absolute simultaneity. No such thing as over there right now. So, what we had after Newton was the onset of what we now call classical physics. And I'm calling this older classical physics because when I get to the newer classical physics, I'll be talking about electricity and magnetism. And these disciplines, like the physics that you learned in high school or college, the science of heat, sound, light, fluid mechanics, going with the flow, vibrations, very important. Vibrations and oscillations are absolutely crucial to old-time classical physics. And so what you have is an arena that explains phenomena like heat, sound, light, and so on in terms of particles and waves. And think of those as two different things. Particles, exactly what you think they are. These little things moving around in space. And waves, we'll have to say something about that. Waves are like this. You've heard of hand waving? That's what I'm doing right now. So you have particles and waves in physical reality in older classical physics. Now when you get to newer classical physics, what I just showed in the last slide is the Newtonian mechanics part of it. And now we get to Maxwellian electrodynamics. And that has its own history. And I'll be reviewing that in just a moment. So we have these two branches of classical physics, the material part, matter in motion, and what we'll come to call the field part of it, electricity and magnetism, electric fields, magnetic fields, and what happens when they get together. There's going to be some waving going on. Oh, we need a philosophical break? Okay, we'll have that. Last time I talked about interpretation of theories, realist versus instrumentalist. I won't repeat that. There's two ways to, well, I will very briefly. I can't help it. There's two ways to look at theories. Either they mean what they say, that those entities that they're talking about really exist, or they don't mean what they say. They're just an algorithm, a bunch of mathematics that allows you to predict other phenomena. What example did I give about? Copernicus, the Copernican theory. This is historic. In the decades between 1550 and 1600, it made a big difference for the historical acceptance of Copernican theory that it be taken in an instrumentalistic way, because there were a lot of people, for a lot of reasons, who were very heavily vested into having the Earth at the center of the universe, and the sun going around the Earth and everything going around the Earth. Talk about geocentric, that's what that means. So it wasn't until Galileo came along, I think I covered this material last time, in the early 1600s, that he said, look folks, Copernicus really meant what he said, got him into trouble with the church, Inquisition. It's all history. So I just was talking about something that I said I wasn't going to talk about too much. Here's what's new. Visualization versus conceptualization in terms of philosophy of science. What do you require in a satisfactory theory that explains what's going on? Should you be able to visualize everything that the theory is talking about? Or can you stop short of visualization and think in terms of conceptualization? That's where the mathematics comes in, because if you have mathematical models and if you're looking for patterns, then you're forming concepts of what's going on, such as the concept of simultaneity that I referred to earlier. You can form a concept of that without necessarily being able to visualize. I mean, we all tend to think that what's going on over there right now has to be something real. I mean, there really is an over there, many light years away, and there really is a right now. But no, you see, according to Einstein, No such thing. There's no such thing as over there right now. So that means that you have to form a concept of simultaneity that stops short of the absolute simultaneity that you were taught by your mother and father when you were 4 years old. That's good. That's good. Visualization. Okay. Next. Now, things are going to get electric here. Electricity. Now, does he look like George Washington? I thought so. In fact, if you look at the year, I mean, maybe they all look like that in 1784. This is Charles Augustin de Coulomb, and this is Coulomb's law. Coulomb's law. Maybe I should use a pointer for this. The force between two charges, Q1 and Q2, is directly proportional to the product of the charges and inversely proportional to the square of the distance. Hey, we've seen an equation that looks just like that earlier. It was gravitation, except instead of having Q1 and Q2, the two charges, you had M1 and M2, the two masses. So two masses in gravity attract one another with a force that is directly proportional to the product of the masses, that's the source of the field, and inversely proportional to the square of the distance. This business over here, these are all constants. You call them constants of proportionality. I'll have something to say about epsilon 0 a little bit later because that turns out to be important. But right now, all that means is that the force is proportional to what you see to the right of the 1 over 4 pi epsilon 0. And this is Coulomb's law. So there. Now, you know, when mathematical physicists say that two equations have the same form, well, just look at this. They obviously have the same form. In the case of gravitation, the product of the masses divided by the square of the distance. In the case of electrostatics, the product of the charges divided by the square of the distance. So you might say that masses, take one of the masses, a mass produces a gravitational field in the same way that a charge, Q, produces an electric field. So now we're starting to think in terms of these masses and charges as sources of a change in the condition of the space that surrounds them. That's what a field is. And the 1 over 4 pi epsilon 0 functions as the constant of proportionality in the same way that that capital G does for gravitation. So you can compare those two force laws, and you can see that they have the same form. Now, we're into electricity. Hans Christian Ørsted discovered that magnetic compass needles are deflected by an electric current. Michael Faraday moved a magnet through a coil, or, if you believe in relativity, the other way around, it's the same thing, and he found that doing that produced electricity. In other words, move a magnet produces electricity. So this is Michael Faraday in 1830, and just 10 years before Hans Christian Ørsted. Next. Okay, watch this. It's very simple. All you've got is this coil attached to a meter, and you're moving a magnet through the coil, and what happens when you move it in and out is you get a deflection in the meter that registers whether or not there's a current. So moving magnets produce currents, and it depends upon whether you're putting the South Pole in first or the North Pole in first.
In which direction?
And well, if whatever the direction is, if you reverse the polarity, then you're going to get the thing deflected in the other direction. Okay, so let's see. So, what is a field? Very important in physics. You have two kinds of fields. You have scalar fields and vector fields. Scalars, magnitude only. Vectors, magnitude and direction. And if it's a field, it has numerical value at every point in space. In the case of a scalar, like temperature, that's all it is. There's a number that corresponds to the temperature here, and one that corresponds here. It needn't be the same. It's a scalar field. It's a temperature field. In the case of, and the same thing holds true for humidity and density. Those things don't have a direction as part of the concept of what they are. Temperature doesn't have a direction. It is what it is. at any given time. With a vector field, you have both magnitude and direction at every point in space. So examples of vector fields would be fluid flow and the electric field and the magnetic field. And I have a picture of what a vector field might look like. So to every point in space, you associate both a magnitude and a direction, and it can have any number of orientations. And just think of it as kind of like something that's going on in a medium and something swirly or something, you know, that's flowing. So that is what a field is. And now we're going to talk about fields. Here's a really good way to visualize a field. Both of those charges, I should use my little pointer here, positive charge, negative charge, when they're close to each other, they attract. And you can almost see how the way those arrows are arranged, that there's an attraction going on between opposites, plus charge and a minus charge. Electricity. In the case of magnetism, it's not plus charge and minus charge, it's north pole and south pole. So here I wanted to give an example of what the field lines look like when you put two like poles close to each other. The same kind of thing would appear if you put two plus charges close together. You get repulsion. So like poles repel and opposite poles attract, and that's the way we represent the field lines. And this holds for both electricity and magnetism. Now we get to ampere, and I don't have a picture of ampere, but we don't need it. All we need here is to look at the main things that he found. And what he found was that there's an interaction between electricity and magnetism. When you have two wires that are carrying current, two current-carrying wires, then each of them forms a magnetic field that goes around them, and it makes for an attraction or a repulsion, depending upon whether the currents are going in the same direction or in opposite directions. Now, so much for when a current is going along a straight line conductor, but suppose the current is going around a coil that's wound up. Then what you get, interestingly, is you get a magnet. You get an electromagnet. And it's the same thing as if you had a magnet with a north pole and a south pole. I have a slide here that shows that very clearly. You see those lines, those field lines. They look exactly the same, but the source on the right is that of a bar magnet with a north pole and a south pole. The source on the left doesn't have any bar magnet there at all. What it has is a current that's going around in a coil, and if it's going around in the appropriate direction, then you get an electromagnet, which is the total equivalent of a magnet that is not hooked up to any electric source. So we're starting to see now, this is part of the classical physics I was talking about. The older classical physics had all to do with mechanics and the phenomena of like heat and light and all of those other things were all based upon principles that came out of Newtonian mechanics. Newton's mechanics was very, very rich in making opportunities to explain all of these other phenomena, but that's all mechanical. We had a mechanical theory of heat. Heat was explained in terms of the motions of particles, and that was all like Newtonian. With respect to optics, that was a little bit different. There were conflicting views about the nature of light. Some people thought that light was made of particles, other people thought light was made of waves, and that's not something that I'm going to be getting into here, but sound, take sound. How mechanical can anything be? What is a sound wave? Why is it that you can hear my voice? It's because there's longitudinal waves in the air that go from me to you that makes it possible for you to hear me. If the air were to be removed from this room, there would be no sound. None. Sound requires a medium. It's a wave. And it obeys the laws of Newtonian physics. So, back to empty space. I'm going to talk a lot about absolute space and empty space. Follow this reasoning. Suppose that space contains electric fields and magnetic fields, or for that matter, going back to Newton, gravitational fields. Suppose you have fields in space. Well, then space has empty space, vacuum. It has physical properties. And two of the properties that it has are what is known in the textbooks as permittivity, which is the ability of a vacuum to support an electric field, and permeability, which is the ability of a vacuum to support a magnetic field. So you have those two very important constants that characterize empty space. This is an interesting case of the contrast between being able to visualize and conceptualization. Because, you know, I mean, I'm talking about empty space. So you would have every right to say to me, if it's empty, thank you very much. There's nothing else going on. I'm saying it's empty space, it's a vacuum, and there's lots going on. There's permittivity going on to permit electric fields, and there's permeability going on, and yet it's still empty space. So what I've got is a concept, or at least the beginning of a concept, but not a picture. Because what the picture yields, if I say space and vacuum, is it yields nothing, literally nothing. So what we're really saying here is that nothing has properties. That sounded funny, didn't it? So let's keep those two things in mind because they're going to appear very soon. Now we come to Maxwell. James Clerk Maxwell, who lived in the 19th century. He was aware of the work of his predecessors, Faraday and the others that I mentioned, and he was starting to put things together to see how electricity and magnetism might be related. So he simplified Faraday's work. He came up with a set of equations that I'm going to burden you with in just a moment. And he already was into suspecting that light is an electromagnetic disturbance. Now that would be really something if it could be shown from the equations. You can suspect that light has something to do with electricity and magnetism, especially if electricity and magnetism are related in the way that they are. And what is light, after all? What is light? Well, that goes back to the business about waves and particles. Are you going to think of light in terms of a wave? Waving in what? Okay, empty space, right? Or are you going to think of it in terms of particle? There's the advantage of thinking of light in terms of particles. You can have particles move in empty space. No problem. You can visualize that. But if you're going to have waves propagating in empty space, you're not going to visualize that because empty means exactly what it says. So you're going to have to be conceptualizing it. And the way I'm urging that we conceptualize things is we lean on the mathematics. If you've got mathematical equations that show you how the phenomena behave, then you have a concept at least. But you have more than that, because if you put it in the form of an equation, and then if you do like what follows from the equation, and suppose it predicts observations that you've never done before, and those observations pan out, then all of a sudden you say to yourself, there must be something to that theory, even though I cannot visualize what that theory is talking about. So, with Maxwell then, he thought that light required a medium for the waves to wave through, and that medium came to be called, in the years after Maxwell, right up to Einstein's 1905 paper on special relativity. It was called the luminiferous ether, or just plain ether. Luminiferous means like the ether can support light waves, is what that means. Is there such a thing as an ether? Do you need to think that there is such a thing as an ether in order for you to believe in electromagnetic waves? Belief is very important here. So, here come the equations, but fear not. We're not going to do anything in deducing. We're just going to say what they mean. Electric field is denoted by E, magnetic field is denoted by B, and these two simple equations tell you what an electric field does. No, actually what it does is this. This is actually Coulomb's law in Gauss's formulation. And that rho there is charge density. And what this is saying is that charge density produces an electric field. Charges produce electric field. Here we have B for magnetic field, and well, what's the source of a magnetic field? This equation isn't going to tell you. This equation tells you that there's no such thing as a magnetic monopole. This equation says, yes, you can have electric monopoles. You can have plus and minus, and you can separate the plus and the minus. And then the other two Maxwell equations connect the behavior of electric field and magnetic field, E and B, this way and that way. The rho is the source of the electric field, which is charge or charge density. And here, that's the function that the J performs. This is current density. So we're to think of magnetic fields as being produced by currents. Currents are moving charges. Things are connected up here. Whereas electric fields are produced by just charges that are at rest. So these are all connected up. So what the physical meaning of Maxwell's equations is that if you have a magnetic field that's changing, well, it's easy to get a magnetic field to change. Take a bar magnet and shake it. The magnetic field around it is going to change. Changing magnetic fields produce electric fields, and vice versa. Changing electric fields produce magnetic fields. And all of a sudden, you're starting to really groove with the idea that electricity and magnetism are two aspects of basically the same thing, and that's why we call it electromagnetic. Now, I have to say something about these mathematical symbols because they have a name that I think at least one member in this audience can relate to. And the name of that symbol is del. And then it's a mathematical operator. Actually, it's part of vector calculus. And if you take del and you make an operation del cross, then that's one thing. Oh my God, I shouldn't get into this. And then the other thing that occurs in these equations is this partial derivative with respect to time. So this is all like vector calculus kind of thing. But I've tried to say enough about what this means physically that you can tell that there might be something to this. Now, the last two Maxwell equations, if in empty space means there's no charge in it and there's no current in it. So if we go back, if we go back to this slide here, that is a source. Make that 0, and you've got empty space. Make the J 0, that would be current density, and that would be 0. And if those two terms are 0, then you end up with this. And if you end up with this, then you see that those quantities that I referred to earlier, mu 0 and epsilon 0, the permittivity of empty space and the permeability of empty space, show up right here in this equation. And if you put those two equations together, which we won't do here, you get this. And those two look exactly the same, and it relates what's going on spatially with what's going on temporally with regard to electric field E and magnetic field B. And these constants are the same in each case. And it turns out that these are wave equations. And what you've done here is you have predicted the existence of electromagnetic waves. Electric waves, magnetic waves. But they're coordinated in a certain very interesting way. This is the general wave equation. It always looks this way. This thing, psi, is whatever might be doing the waving. It could be electric field, magnetic field, and it could be, are you waving? Well, then you'll have to obey this equation as you do that. So whatever is waving is the psi, and the v that occurs here in the reciprocal of the square of the velocity is the speed of the wave. So this is a general wave equation. And here, you have wave equations, one for the electric field, one for the magnetic field, and they both have exactly the form of any wave equation at all, whether it's mechanical, acoustic, whatever. That's the general wave equation. Now, interesting thing is, you got the mu 0, epsilon 0 here, and here you have 1 over v squared. What does that tempt you to want to do if you're mathematically inclined? If you're physically inclined? If you're inclined both ways, it makes you want to set 1 over v squared equal to the product of mu 0 epsilon 0. You want to make that identification in order for those equations to agree with one another. And if you do that, then you've done this. And if you've done that, then you have predicted the velocity of an electromagnetic wave. It's 1 over the square root of the product of the permittivity and the permeability of empty space. This is really happening. Light can travel across space in a vacuum. And these quantities are kind of like properties of empty space. And the speed, this is the speed of light. Speed of light. Hey, wait a minute. I thought we were talking about electromagnetic waves. You crunch the numbers. It's the speed of light. So Maxwell knew that light is an electromagnetic wave, and I consider that to be deep. Why electromagnetic waves? They exist because if you change magnetic fields, it produces electric fields, which in turn produce changing magnetic fields, which produce changing electric fields, and on and on and on. So you get waves that are propagating through empty space. They're very similar to sound waves and water waves, but sound waves have air as a medium. If you took the air out of the room, you wouldn't be able to hear me talk, and that would be bad. Water waves have water as a medium, so you can make waves with water. Electromagnetic waves, sometimes they have a medium, sometimes they don't, but guess what? They don't really need it. They can propagate in empty space. And so you might regard that as miraculous, but not many members of this audience want to go that way. So, electromagnetic waves. Now, this is interesting. Light is an electromagnetic wave, but light is only a tiny sliver of all of the electromagnetic waves that exist. And it goes from long wavelength electromagnetic waves, like radio waves, microwaves, and then just to the left of the visible spectrum, which goes from red to violet, you have infrared. Those are all electromagnetic waves, and the only way they differ from one another physically is their wavelength or their frequency. Well, wavelength and frequency are just the reciprocal of one another anyway, so we're talking about the same thing. So these are the long wavelength electromagnetic waves. Here we're right in the middle. These are all the colors that we can see, and the explanation of why there are different colors is because they have slightly different wavelengths. So the wavelength of red light is different from the wavelength of blue light. And violet is over to the end of that visible spectrum. So then you get ultraviolet, a very real thing, ultraviolet. I mean, you get a sunburn, you know it, right? And, but you can't see ultraviolet. You can't see it as a color. Then you get X-rays. We've all had X-rays. And some of us have even had gamma rays, especially if you're in an area where there's nuclear fallout. Anyway, so this is the electromagnetic spectrum, and this is something that Maxwell's equations explain, the whole shebang.
And with these laws, Maxwell could show that electromagnetic waves of every frequency and wavelength would propagate through empty space at the speed of light.
I'm sure that from now
Maxwell's discovery, which seemed purely theoretical at the time, would lead to the sights and sounds of the 20th century, radiating through space not only as visible light, but also as radio waves, microwaves, and the entire electromagnetic spectrum. It was a discovery that would lead far beyond the Earth into the deepest reaches of space, where a wave in the intensity of the electric field implies the existence of a changing magnetic flux. That means a wave in the magnetic field. And that's made possible by changing electric flux. And it's made clear only because Maxwell understood that electric and magnetic fields create each other if they move in a wave together at the speed of light. And so it goes. in lockstep through eternity, both fields propagating throughout the universe.
This is interesting. The electric waves go like this, and the magnetic waves go perpendicular to that, and they're both like headed in the same direction. And that's what electromagnetic waves are all about. Now, let's see what we have coming up here. We had to get to him, didn't we? You know, this is something that may not be well known. I guess some people in this audience might know this already, but this is the first paragraph in Einstein's first paper on relativity. It's Special Relativity. It's 1905. And the title of that first paper on relativity from Einstein was On the Electrodynamics of Moving Bodies. If you only knew the title, you'd say, is this supposed to be relativity? Might be interesting. It's Einstein. It's a young Einstein, too, as you can tell. So I'm going to read this to you because this is going to directly relate to what we just saw. Let me read it off of here. It is known that Maxwell's electrodynamics, as usually understood in the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. Now, that's something that we saw, you know, in a previous slide where we had a coil and we had North Pole, South Pole going through. That's exactly what he's talking about. I'll show that again in the next slide. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. You know what he's driving at. This is Einstein. He's driving at relativity, and he's saying all that really matters is the relative motion of the coil and the magnet, whereas the customary description would describe it in a different way, but in terms of anything that you can observe, it's the same. So let's see. There. It's this thing here. So what I can't go back now to the video, but it's fairly clear. That coil can be at rest. That magnet, North Pole, South Pole, can move through it. So if it's moving through it, something is happening. But suppose, just the opposite, suppose you hold the magnet steady and you move the coil instead. What's the difference? Do you believe in relativity? There's no difference. And so what will happen on that galvanometer, that meter that shows, you know, what current is going on, will be exactly the same. So I have to tell you what relativity is, and we'll wrap it up very quickly so that we can have time to, you know, comment and question on any of this. There are really three kinds of relativity. One is classical relativity that goes back to the time of Galileo and Newton. And what that said was, this is before the laws of electricity and magnetism were discovered. So what they knew about were the laws of mechanics in the 17th century. And then in the following centuries, what I showed you in an earlier slide is that when thermodynamics, the science of heat, sound, light, optics, all of that, all came out of Newtonian mechanics. And this is all classical physics step one. And classical relativity says that all of those phenomena that depend upon the laws of mechanics are the same whether your frame of reference is at rest or whether it's moving at a constant velocity. It's the same. So for example, if you're on a ship and you want to play ping pong, if the ship is at rest, play ping pong, no problem. Suppose the ship is moving at 20 miles per hour and it's a perfectly smooth sea, and just to put an emphasis on it, you go down where you can't see anything. You can still play ping pong. I mean, it's the same thing. It's the same thing. All the phenomena of mechanics, of the matter, motion of matter, happen the same way in a frame that's moving at constant velocity than it does in a frame that is at rest. And there are the two frames. I think I accidentally advanced the thing, but I had to do that anyway. So there are reference frames, and now hang on, because this is going to look too equation-y, but we're at the end of this. Transformations. It's not too bad. The Galilean transformation says that if you go from one frame to another, and you can tell it's going in the x direction, the x prime in the moving frame is the x in the O frame minus velocity times time. It's just freshman physics, and that's all that is. And as far as time goes, time is absolute. T prime equals t. Time in the in the moving frame is exactly the same as time in the O frame. But now, the Einsteinian transformation, which for historical reasons is called the Lorentz transformation, can't go into that now, looks like this. This almost looks like that, except that it's got this funny little gamma factor in front of it. And this also has a gamma factor in front of it to go, you know, for the time transformation, but it has something even weirder. It has this expression, velocity times distance divided by the square of the speed of light. This is the Lorentz transformation. We're not going to go into that, but the important thing is that the kind of a if you wanted relativity to hold with regard to not only the old classical physics, but also the new classical physics that involved electrodynamics, you needed this Lorentz transformation, and you had to give up the old transformation, and therefore you were giving up absolute time in favor of this new conception of time. Now, the other thing that's interesting to notice, and this is exactly what you would require, what you would expect and what you would require, if you look at this gamma, just that gamma factor right there, and if you have V much, much less than C, then this becomes 1 divided by 1 minus something that's almost 0, and that means that the gamma becomes itself 1, and this becomes 1, and that becomes 1, and this transformation, which is the Einsteinian one, reduces to the Galilean Newtonian one that you had before, in the limit when you're into slower velocity. And when I say slow velocity, you know, you can be going pretty fast. I mean, these phenomena that happen as a consequence of Einstein's special theory of relativity only really show up once you're considerably past half the speed of light. Now, light travels at 186,000 miles a second. That's very, very fast. And so our ordinary experience doesn't see a lot of these so-called relativistic effects just because the speed of light is that fast. Now, can you tell when we're wrapping up? Did you know that Einstein, you know, I mean, he did write E equals mc squared on his blackboard, but then he erased it and he wrote something about humanism. And so now we're going to finish up with two quotes, and I think they kind of relate to what we've talked about before. And these two quotes are from the 20th century physicist Paul Adrien Maurice Dirac, one of the founders of quantum physics. And Dirac actually said this. And you might be surprised that a physicist would say something like this unless he was really heavily into the beauty of the mathematics that he's using to describe physical reality. Dirac said it is more important to have beauty in one's equations than to have them fit experiment. My goodness. What is empiricism all about? What is science all about? It's got to fit experiment. He says, no. It's more important to have beauty in your equations. Okay, that's fine. It's Dirac. I'm not going to argue with that. The other thing that Dirac said, and maybe we can puzzle this one out. Now, this is very interesting. He said, in science, one tries to tell people in such a way as to be understood by everyone something that no one ever knew before. In poetry, it's the exact opposite. We have time for comments and questions and things like that.
I keep thinking about the equation you showed, and I don't remember every term, but it was over the square root of the product of permeability and what was the other term?
It's called permeability and permittivity.
And I kept thinking, are those quantifiable things?
Permeability of empty space. So it's allegedly a property of empty space, and you can determine what that is by fiddling with the right kinds of equations. It's something that you infer that empty space must have in order to be able to sustain a magnetic field in the case of permeability. And the epsilon sub-zero is the permittivity of empty space, and that is also empirically determinable. And it's kind of neat because once you, I can't reproduce for you how it's exactly done, but they do it. It can be, you can run some experiments and find out what those two properties of space are, multiply them together, take the square root, take the reciprocal, and lo and behold, as if by miracle, you get the speed of light.
Why did they squared why was del squared? I mean,
Okay, well, the del itself would count as kind of like a first derivative, and the del squared means that it's a second derivative. And if you're going to get a description of waves, you're going to be doing second derivatives with respect to space and second derivatives with respect to time. Otherwise, no waving.
Okay, when I try to relate this concept of equations to the simple things that you showed in the video, like I'll start with the bar magnet. It's got a magnetic field, which is B on your shirt there, and I see 3 equations about B, and they've got electric field. One says B del dot, the source, there's no source of magnetic field lines. One says that, oh, they wrap around based on electric current, or electric field, and the other one says, you know, they depend on electric current and the rate of change in the electric field. None of that stuff's happening in a bar magnet. What's going on that you haven't you haven't explained the real simple thing there about?
If you move a magnet, you're going to get that kind of action.
The organized structure of the iron, if you cool iron in the presence of a magnetic field, it will take on a magnetic structure. And this is how they tell when there's been changes in the field on the Earth, and that there was a change at some points and different points in time.
I don't know how to ask the question, but it seems like these waves have to come from somewhere, and maybe that what he said has something to do with it. It seems to me there has to be some action someplace to make a wave. So where does the original action come from? So is there some place where if there was like no sun or no, I guess if he has physical matter and it's moving, it creates a wave. Like he said, if you have iron and you move it, it creates a wave. I don't understand where the original wave is. There some place where there is no wave?
Okay, the original equations, the Maxwell equations, show the source of the waves in terms of a charge density and a current density. Current is a moving charge, so the whole basis of everything comes from moving charges. Take a charge, move it, and you have electromagnetic waves. That's the source.
With all of the concepts that you walk around with every day, the ones you've explained, how do you make sense of the practicality of living? I mean, do you think in terms of formula when you go grocery shopping? Do you think in terms of the universe? Do you think there can't be something going on now when there might be something going on somewhere else? Do those kinds of thoughts influence how you are practical in your everyday living?
Yeah.
I mean, you have an incredible sense of humor. You take pride in that. How does that fit with mathematical formula?
You know, I'll bet someone has written there is such a thing as a mathematical joke, but to get to what you're saying, I mean, you know, this compartmentalization in life, I mean, geez, you know, you can ask my children, ask Joanna. I don't, that's not what I think and talk about every day. It took me a long time to get this act together. And
the father of quantum mechanics or quantum physics.
Direct.
The notion that beauty was far more important than the function of the formula.
He said
What's
that.
going on with that? I mean, how do we how do we quantify beauty? You can't.
There are people who are involved in either pure mathematics or the applied mathematics that physics describes that have a sense of aesthetics when it comes to the material they're dealing with. And they can tell when there's beauty in equations and when an equation is in their... it's a very subjective thing, I think, admittedly. Yeah.
One thing that's interesting to me is the proposal of this ether way back when that some of the scientific investigators were positing. And it seems like maybe ether is, that part of that concept of ether is in space, that space does, we're finding, have energy, that space is expanding over time, that distance is involved in some of these equations. So it's interesting to me that that the concept of empty space doesn't really hold, that space can never be empty, that space has properties.
That's interesting you say that, because I think that modern quantum field theory has space filled with something that's quantized. And so it could very well be that that old intuitive notion that completely empty space just makes no sense. I mean, you could take the air out of this room and there would still be a lot going on, physically speaking. And so what does perfect emptiness mean? It could be that it's a meaningless concept. And I think that modern physics does not entertain the notion of a true vacuum anymore. But it's an interesting thing. In the night, when Maxwell was doing his work, he absolutely required a mechanical medium that he called the ether. And it wasn't until Einstein came along in 1905 that said that we can do without that.
I was thinking about what Derek was getting at in saying that that beauty was more important, and I kind of get the idea that for mathematicians and physicists, unification is a beautiful thing. It involves you end up with very simple mathematics, and it's easier to understand, and the whole picture all of a sudden is clear. You know, sort of like you know, Euler's equation that united square root of -1 and pi and all these things in one really simple little equation.
Interesting you mentioned that, because that's a different kind of unification, that Euler thing about e to the I pi equals -1, purely mathematical kinds of things, nothing to do with physical reality directly. Whereas what we're talking about is the kind of unification that's going on. I mean, it's kind of, you know, relating electric fields and magnetic fields and vice versa. And it brings together things that people used to think of as being separate. And then the real payoff is that when you bring electricity and magnetism together in that way, and you say, gee, really, change this electric field, make a magnetic field. Change the magnetic field, produce electric field. And then, almost as a bonus provided to you by the Lord Almighty, you get an explanation of light. All of a sudden, just because electricity and magnetism are related in that way, you see light as an electromagnetic wave. That's the biggie. This is my key prime example of what constitutes a deep explanation in physics. And I don't know any other discipline that can produce explanations quite like that. And you've got to have the math to do it.
I'll try to make this brief. So obviously during Maxwell's time, they considered the ether as a potential theory that would explain the connection between celestial bodies. Now, today we understand gravity plays the majority of that role. But with the possibility of dark matter, do you think the combination of dark matter and gravity essentially provides some basis for the concept of ether?
Can be. The whole business with dark matter didn't come up until very many decades later, and so nobody knew anything about the existence of that kind of thing.
Laurent just finished part 2. He needs to talk about part 3 to bring you up a little bit more towards answering the questions that you're asking. For instance, the light, people are looking at this wave as being from there to there. Actually, it's a chunk of energy which is moving through space as a photon. It is not a continuous wave from there to there. It's a little chunk, and it's waving within itself as it moves. So Laurent will have to give us a part 3 to bring us up to the 21st century.
Thank you.
Thank you, Laurent. That was